Hello everyone, myself Dr. Anju Mishra, and today I'm going to take up the topic of fuzzy systems and inference. So as we know about the fuzzy systems, fuzzy refers to the things that are not clear or are inherently vague. So when we talk about the vagueness in daily life, we can say that unlike the crisp logic, there is not every situation where we can answer and represent the domain problem with the help of yes and no kind of outcomes or the decisions, right? So sometimes the decision or the outcome needs to be in between the yes and no, unlike the um, crisp set, where either the outcome belongs to the set or it does not belong to the set. So when I say, for example, that a person is having the fever, so or a person is having high fever, for example, if I'm going to represent this thing in the crisp logic, it could be represented as either yes or no. But sometimes in real life we see that the situations are not that deterministic, and there are possibilities between yes and no, where we could be in a state where I cannot 100% guarantee whether the person is having high fever or not. It could be high for somebody, it could not be high for somebody else. So that way there are certain outcomes that need to be considered between these two limits. So when I, for example, say that the temperature is hot or not, for some people it could be hot, for some people it could not be hot. So in those situations, it is more convenient to represent your information using some other kind of logic, which is suitable for representing this type of domain information. So to deal with the vagueness and this kind of situations where we are not 100% sure that whether a particular outcome belongs to a specific category or not, or sometimes we may be like quite unsure that how much this belongs to a specific category, or we think that the same outcome belongs to different categories with certain degrees of association. Then in that case, fuzzy is the best thing that we can use to model our system. So as I already have said that in real world we need to check whether a particular state is either true or it is false. So we are always talking in terms of true and false, but we are not able to handle the vagueness effectively when we are dealing with the crisp modeling. So in that case, fuzzy can provide flexible reasoning, and it can handle the vagueness of a particular domain. And in real time or real life, there are many scenarios where we are dealing with the vagueness of the system, and so we want to incorporate that vagueness into the model, so that the real world problem can be effectively addressed, and it can be effectively represented in the computer system. So by using the fuzzy logic, we can deal with inaccuracies and uncertainties of any situation. So now when we talk about the fuzzy logic, it is a multi-valued logic. So multi-valued means we are not only having values between we are not having only values as 0 and 1, rather we are taking a range between 0 and 1. So we are picking up multiple values from between 0 and 1, and that way we say that fuzzy logic is called as a multi-valued logic. Now the variables here that are going to be used, they may be any real number between 0 and 1, unlike the traditional values of the true and false. It is used to deal with imprecise or uncertain information. So mathematically, we have methods in fuzzy system or in fuzzy inference or fuzzy logic that can deal with the imprecise or the impreciseness or the uncertainty inside the particular decision making system. Now the frequent applications of fuzzy systems is in control systems. So we can design control system effectively with the help of fuzzy system, and we are going to see certain examples on how fuzzy are going to create models for us, and solving those real life problems more effectively than the traditional way of building models. And apart from control system, we can also do the image processing. So there are certain impreciseness and vagueness in while dealing with the image processing domain, where we need to deal with the information stored inside an image, and that can also be processed uh, more effectively by using the fuzzy logic. Apart from that, natural language processing is another domain where fuzzy are very popular, and they are providing more robustness to the language processing task and other thing, and they are able to model the natural languages more effectively than the conventional approaches. Next field is called as the medical diagnosis. So again, as I already have given one example, in medical diagnosis, what happens that that we are checking certain parameters or certain patterns from the patients, and based on those parameters, we need to decide that whether the person is having a disease or not. Now, the disease could be at different level. So sometimes it is the patient is having disease, but the disease is not that much dangerous or in a very severe state. So in that case, we need to take certain actions. So of course, we cannot say that the person is having the disease if symptoms are not there. Sometimes the symptoms are not that much visible to the person, but internal parameters are indicating that the disease is present. So in that case, if you are using a conventional model for disease diagnosis or something like that, then in that case you may not get correct decisions for your patients. So that time, to handle the vagueness and the impreciseness inherent into the domain knowledge or the domain itself, in that case fuzzy systems are proving more accurate in providing the diagnosis and the prescriptions to the patients. And last, we are having the AI domain, where fuzzy systems are taking over, and we can see that there are many models which are hybrid, where the conventional machine learning and the fuzzy systems, they are being combined, and those hybrid models are going to be used to solve the problems using the hybrid approaches. Now, the fundamental concept or fuzzy logic is the membership function. So, when we talk about the membership function, it is actually the characteristics of a set. So, if I say that we are having a crisp set, so for example, if I have a universe of discourse, for example, denoted by X, and I have, for example, a set from this universe of discourse called A, which is having certain elements 1, 2, 3 like this, right? And now, for example, if I need to define a membership function here, so for example, if I have one element like 3, so for this 3, my membership function will be able to answer whether this element belongs to this set A or not. So in this case, you can get the answer in a crisp term, where you can definitely say that yes, 3 is present here, definitely. So it is definitely there. It is giving you an answer as 1, means your element is present. But for example, if I talk about another element, which is, for example, 4, and suppose 4 is not listed here in this set, then in that case, you are getting answer as 0 using your membership function here. And this membership function states that 4 element does not belong at all to the set A. So in crisp terms, the fuzzy membership function, this crisp membership function is one function that maps the output to either 0 or to 1. But in case of fuzzy logic, the membership function is different, and it defines that how much degree of membership or how much belongingness a particular element has in a particular set. So the membership function is a mapping from an input value to a membership degree between 0 and 1. So this degree determines that how much or with how much confidence I can say that a particular element belongs to the set or it does not belong to the set. So here, as we see that 0 represents the lower limit or lowest degree, and 1 represent the highest degree of membership, right? So in between also, we can have multiple values. So for example, there could be a possibility that a particular element, for example A, can have a membership of 0.5. So with 0.5 or 50% confidence, I can say that this element belongs to the set, right? So this is a kind of fuzzy membership, and fuzzy sets again are the sets which are having elements into it. But the difference here is that for every element we are having a degree of membership for that particular element into the set. So this is the fundamental about the fuzzy systems or fuzzy logic. Now we talk about the fuzzy rules. So fuzzy rules are the rules which are going to help you in modeling the system and to extract the inference. So for inference procedure, we require fuzzy rules. And how we are going to formulate the fuzzy rules? So they are nothing but the if-then statements that we need to create. And these if-then statements, they are used to express the relationship between the input variable and the output variable, right? So for every input and output mapping, I need to create certain fuzzy rules, and those rules will be going to be fired whenever the if condition is going to match up with the input, and that way some inference will be done by the system, by the fuzzy system, and you will be getting a certain outcome or the output. The output of a fuzzy logic system is a fuzzy set, which is a set of membership degree for each possible output value. So as I already have discussed here, that the output also is a fuzzy set. In case of fuzzy systems, we are not getting a crisp value, rather we will be getting a fuzzy output, and here the elements are having, or the output is having, a membership degree for each possible output value. So this is an example of a crisp system. So as you can see in crisp system, if I need to answer the question whether the temperature is hot today or not, there are only two possibilities that we can deal with. One is called that temperature is hot, so we can say yes, or we can say no. So only two answers I can give, yes and no. But what about in between? So sometimes as you observed, it is not like that. As humans, we are answering the questions always in terms of yes, no. Sometimes we say the temperature is hot, sometimes we say that no, it is warm, sometimes we say that the temperature is cool, right? So here, as you can see, that we are having varying degree for the temperature, and we are using certain linguistic terms here. So these are called as linguistic terms. Linguistic terms that we are using here to determine what is the characteristics of this parameter called temperature right now. So I can say the temperature is hot, I can say the temperature is warm, I can say the temperature is cool, right? But how much temperature represents the cool, how much temperature range represent the warm, how much temperature range represent hot? There is no definiteness here. So I cannot always say that only 20 degrees centigrade or 15 degree centigrade represent cool, right? For some people 15 could be cool, for some people 20 is cool, and when temperature goes down and it reaches to 15 degrees centigrade, it could be very cold, or cold for some other people. So in real life, person to person, this, value for these cool, warm and hot parameters, it is going to be changed, right? For some people, even 23 degree could be very hot. For some people, it could be warm only, right? So depends upon person to person that how this, hot, warm or cool we are going to use. And in real life, we are not every time, telling the exact value of the temperature, that today's temperature is, 35 degree or something like that. In real life, we mostly use these linguistic terms as temperature is hot today, or it is very hot or sunny today, right? So fuzzy logic actually attempts to model your system as we deal with it in the real life scenarios. Now, the architecture of fuzzy system is important to understand, and today we are going to take up the different components of a fuzzy system. So when you are going to create a fuzzy system, what different components we need to consider, that we will discuss here today. So in the architecture or of a fuzzy system, we are basically having 4 different components. The first one is called as a rule base. Then we have a fuzzifier. Then the third component we have is the inference engine. And then finally we have another component which is called as a defuzzifier. So when we talk about the rule base, as I already have told you, that for doing the inference, or inference is nothing but mapping the input to the certain output. So this input output mapping is being done with the help of the rule base here. So as you can see, that rule base is one of the important the component here. Now, why we say that it is a rule base? Because we are not having a single rule here, rather there could be a collection of rules. So we are having a collection of rules, fuzzy rules here, which is stored inside the rule base of a particular domain problem. Now, the fuzzification, inside the fuzzification or the fuzzifier, we are doing the process of fuzzification. So fuzzification means that you are receiving a crisp input, or you are having a crisp input with you. Now, before doing the inference by the fuzzy system, you need to convert this crisp input into the fuzzy input. So you have to convert it into fuzzy representation. So your input need to be converted into fuzzy representation. Then only the fuzzy system will make inference on this input, and it will give you certain output. So this is a precondition that we need to understand, that the crisp input cannot be directly provided, or cannot be directly used for doing the inference using the fuzzy inference engine. For this, we need to perform a certain kind of a pre-step, which is called as a fuzzification step. So fuzzifier is the module that does the fuzzification, and it converts the crisp input into the fuzzy input. Once your input is being converted into fuzzy representation, then it will be used for doing the inference. And inference engine is the component which is responsible for looking for the rule base and performing the inference. So all the processing part here, which converts the input into the output, that is being done with the help of the inference engine component, right? And inference engine requires the rule base as well as the fuzzified input. So with the help of these two components, the inference engine is working or doing the processing. The last component here is the defuzzification or defuzzifier. The defuzzifier is a module which is responsible for converting the fuzzy value or fuzzy output to the crisp output. Okay, right? So for example, I can say here that for example, if you are doing fuzzy inference, so in that case the output will always be generated as a fuzzy set with the degree of membership of the output, right? Now, once this fuzzy output is generated, you need to convert it back into the crisp output, so that you can set your controller, or you can set for example the temperature, or your AC, for example. So your air conditioner one, for example, if you are designing a fuzzy control system for your air conditioner to control the temperature, right? Now you have created a fuzzy system. So the output is coming here, or the inference is coming here, that the user wants a cool temperature. Now, since the air conditioner requires certain specific temperature value, so you cannot simply say that set the temperature to a value cool, right? It requires certain crisp value for the temperature here. So you need to convert this cool into some temperature value which is in crisp terms, right? So I need to specify that how much cool is required, or how much temperature represents this cool output. So for example, if I say that to cool, set the temperature to 16 degree, right? Okay, so this is the responsibility of the defuzzifier to defuzzify the output which is in fuzzy form back into the crisp form, so that the control system can work according to these values generated. So we already have discussed that rule base is the one component which is responsible for containing the set of rules which are nothing but the if-then conditions and provided by the experts for the decision making system, and these are based on linguistic information. So for example, if I need to do, or I need to create a fuzzy rule, it will be like, for example, I need to write if, for example, your temperature equals to cool, and okay, so if I need to write, for example, and the air pressure, equals high, then set, so some variable you can set here, or you can say that weather will be windy, for example. Okay, so this way the rules are created in fuzzy terms, and as you can see that we are using the linguistic values here to reflect the values for these parameters like temperature, air pressure, and weather. So you are not specifically setting the temperature to 18 degrees centigrade, air pressure to some numeric value. Rather, you are using linguistic values here for your variables, for your fuzzy variables, and then you are making these rules, and these rules will be used for doing the inference. This we already have discussed. Thus, fuzzifier is the one which is responsible for creating the or converting the crisp input into the fuzzy input, and defuzzifier is just the reverse of the fuzzifier, where you are converting the output which is in fuzzy form back to the crisp form, right? So this is the architecture of a fuzzy system. As you can see that the rule base is interacting with the inference engine, and with the help of the fuzzifier and the rule base, the inference engine is able to do the inference here, and it will be generating certain fuzzy output, right? So here the output you are getting out of this will be in fuzzy form or fuzzy set, right? Now the defuzzifier is responsible for converting this to the crisp output. So when I talk about the membership function in case of fuzzy system, it is represented as a graph that defines how each point in the input space is mapped to a membership value between 0 and 1. So there are three types of fuzzifiers that we can have with us. One is called as the singleton fuzzifier, the other one is a Gaussian, and the third approach is called as the trapezoidal or triangular fuzzifiers. Most of the time we use the trapezoidal or the triangular fuzzifier or fuzzy membership functions frequently in the real life scenarios, or solving the or building up the fuzzy models for the real life problems. So as you can see, the membership function defined here is as mu a, right? So mu defines the membership function, the fuzzy membership function here, and a is the fuzzy set. Okay, sometimes we define a crisp set as A and a fuzzy set as A with a tilde. Okay. Now, X is the universe of discourse and it is having a range of 0 to 1. So, each element of X is mapped to a value between 0 and 1, where 0 and 1 are inclusive. It is called membership value or degree of membership. It quantifies the degree of membership of the element in X to the fuzzy set A, as we already have discussed. X-axis of the graph represents the universe of discourse, while Y-axis represents the degree of membership in the 0-1 interval. So, we are going to see one membership function, which is a fuzzy membership function here. This is one example. As you can see that this axis, for example, representing acceleration values, and the y-axis represent here the membership function. So, we can see here that we are using the trapezoidal or the triangular, fuzzifiers here to represent the membership of every, linguistic value. So, you can see the first trapezoid, this represents the range between 0 to -5, okay, and it says that if your acceleration is between 0 to -5, we are going very slow, and if the acceleration value ranges from -10 to 0, then we are going with a acceleration of very low. The 0 represent, okay, 0 represent a 0 acceleration, but it is not a crisp value here. So, you can see that this triangular function represents here that the value between -5 to +5 for acceleration is treated as having almost negligible acceleration for a vehicle, right? Similar case, you can see that for the high value, we can have 0 to +10 of acceleration. So, you can say that the vehicle is moving faster or with high acceleration. And if it is, going from +5 to or more than +5, then we can say that the acceleration value is very, very high. So, there are certain advantages of fuzzy system. They can work with any type of input, whether it is imprecise, distorted or noisy. The construction of fuzzy logic system is easy and understandable. The next advantage is that it comes with mathematical concepts of set theory, and the reasoning of that is quite simple. So, it is easier to model the domain information in the form of fuzzy models. It provides a very efficient solution to complex problems in all fields of life, and it resembles human reasoning and decision making. So, thereby, whatever problems we are having in real life, those can be directly converted and be represented with the help of the fuzzy systems. The algorithms can be described with little data, so little memory is required. Now, there are certain disadvantages. So, different researchers have provided different solutions, which leads to some kind of ambiguity. So, there are certain representational ambiguity inherent with these fuzzy systems because of the work of the different researchers. So, that need to be clarified once you are using. So, which is the standard format that need to be considered here. There is no systematic approach to solve a given problem using the fuzzy logic. Another disadvantage is that the proof of the characteristics is difficult or impossible in most of the cases. So, every time we do not get a mathematical description of our approach, as fuzzy logic works on precise as well as imprecise data. So, most of the time accuracy is compromised. So, this is all for today. Thank you.